Okay, we're live.
Welcome everyone to the TUM AI lecture series. It's a great pleasure for me to introduce today's speaker. Today we have Rick Szeliski with us. He's a very well-known researcher in computer vision and computer graphics. His career spans many years of amazing contributions. He's an affiliate professor at the University of Washington, member of the National Academy of Engineering, and fellow of the ACM and IEEE. He's very well known for his works in the fields of computer vision, image-based modeling, image-based rendering, and computational photography. And he's one of the pioneers in our field, and he's known for many, many works, in particular works like phototourism, photosynth, hyperlapse. Many of these technologies have gone into products. Actually, part of this success is due to the fact that Rick also spent many years in industry. He's been with Microsoft for around 20 years, and he then joined Facebook as founding director of the computational photography group in 2015, and just recently retired. His works are seminal, they're very well known, and so he's definitely one of the big pioneers in our community, and so it's a great pleasure for us to have him here today. Rick, the floor is yours.
Thank you, Daniel. Thank you for that very gracious introduction. I'm very excited. It's been an amazing lecture series, just looking through some of the previous videos, lots of speakers. As I'll mention later, a lot of the speakers are talking about their latest work in neural rendering, and that's something I'll touch on near the end of my talk. But basically, it's been about 25 years now since the term image-based rendering was invented. Two of the sort of foundational papers, the light field and the Lumigraph, came out in 1996. And today's talk is less of a research talk and more of a tutorial on the sort of 25 years of image-based rendering. Because if you look at the latest papers, they reuse a lot of the same ideas and foundational principles in vision and graphics that have been in the field all along. So you will notice a lot of overlap between today's talk and the talk I gave at the tutorial at CVPR. So as Daniel mentioned, I happily retired in December. Unfortunately, before I can completely devote my time to my personal interests, I still have to finish writing the second edition of my book, which I've been working on for 2 years, but it's almost done. And it contains new material. In particular, there's a new chapter on deep learning, which wasn't there in 2010 because those techniques really weren't state of the art. And it's early on in the book because deep learning is used throughout in other techniques now, like multi-view stereo and even image-based rendering. So the recognition chapter has moved up early because a lot of students want to do recognition only or want to do a project in it. And today we can basically do a lot of recognition without ever using techniques that involve three-dimensional modeling and segmentation, things like that. Everything's done end to end. The chapter I was just working on for the last week was finishing up the one on image-based rendering, and in particular the section on neural rendering. So as I'll mention later, there's some great survey papers out there, but there's also a ton of new publications, new papers coming out every month. So I'm only going to really mention them briefly because a lot of this has been covered in previous lectures. So what I'm going to cover today is kind of a review of some of the basic principles and some of the applications in image-based rendering. So I'll start with a classic computer vision technique, which is multi-view stereo, and then talk about some of the foundational representations that people have used for image-based rendering, things like Lumigraph and light fields and sprites with depth, sometimes known also as billboards, and layers, which are now really very popular with the multi-plane images. I'll show you an example of how we can put these things together to create and compress and transmit interactive 3D video. That's the virtual viewpoint video work, which we did back in 2004. And I'll talk about other kinds of augmented video, 360 video, where you can look all around, and 3D video, which is sort of a continuation of this virtual viewpoint video. And then I'll mention something which now you can have in your own pocket, which is 3D photos. If you post your photos on Facebook or share them on Google, you can now take a regular photo and turn it into something that is interactive and three-dimensional. So just to sort of show how these 2 decades of research have now gotten to the point where the algorithms can run in your pocket, due to many advances in computer vision and neural networks as well. The reason I put reflections in the title of my talk is not just because it's a retrospective on 25 years, but I also feel that modeling reflections, the kinds of things we see when we're looking through a shop window or something like that, is still a somewhat understudied area in image-based rendering. So I want to talk about some approaches we've looked at for this technique and mention some of the limitations. And then at the very end of the talk, I will talk briefly about neural rendering, mostly about 2 projects that I've been involved in. I've been very late coming to the neural networks game. I really didn't do any research in the area until recently, but I've been very excited to join some other researchers who are working in this area. And I'll show you 2 projects we've done for taking still images and turning them into 3D walkthroughs and short animated clips. So, because it's an online lecture, there's less opportunity for questions. Normally during a class lecture or a personal lecture, I ask people to stop me during the talk. But I suspect that's going to be harder, but definitely communicate with the organizers any questions you might have, and I'll take them at the end of the talk. So let's start with a quick review of multi-view stereo. Stereo is a topic that's been studied since the 1970s. The picture on the bottom is one from a multi-view stereo paper that I worked on when I was a graduate student at Carnegie Mellon with Takeo Kanade and Larry Matthews. And we would take a series of images and extract a depth image, and then you can paint the input image, one of them, onto the depth map, interpret it as a 3D mesh, and look at it from different points of view. So in computer vision, we were already doing this kind of view interpolation. The seminal paper in SIGGRAPH was by Chen and Williams in 1993, where they showed that if you capture or pre-render a bunch of high-quality images, then by knowing what the depth map is, you can basically move the pixels around and do smooth view interpolation, which means that for fewer images that you have to compute, you can actually get a smooth camera motion. Some follow-on work to that was this view morphing paper by Steve Seitz and his advisor, where you could take a pair of images like the one on the bottom left and generate a new in-between view, or he was even able to take a picture of the Mona Lisa, and by flipping it sideways, he basically got what would have been a view from a different side, and he was able to do that in between animation like this. Half a decade later, we actually applied this to video. I'll talk about this video view interpolation system a little bit later. And people have built other systems that take video and interpolate the camera move. In particular, it's been popular at sporting events like the Super Bowl, where by putting a ring of cameras around the stadium, they can basically now move and have an in-between view to get just the shot they want for a particular play. And Takeo Kanade has worked on this for decades. He called this project virtualized reality. Yasser Sheikh at CMU is continuing that work, calling it the panopticon. But basically, you can capture people inside a sphere, and potential applications are things like instructional videos. Watching a pro do a good golf shot. So the basic mathematics and geometry behind multi-view stereo can be described in many ways, but one way that I really like is called this plane sweep approach, where let's say the left and the right images are 2 images you're trying to match, and you will put a virtual camera in the middle, and then what you'll do is you'll say, what if I actually had a 3-dimensional plane in the scene? What if I swept the plane and replaced the cameras with projectors that were basically projecting the light back onto the plane? And so each of the planes in the world defines a homography, which is a kind of parametric image warp between the input image and the actual virtual camera. And so as you sweep these planes, you basically get the images either lining up or not lining up. An easier way to see this is for a horizontal camera motion. If we basically just shift all of the images together, you'll notice as I'm shifting, the trees in the background come into focus. And if I kept going, eventually the tree in the foreground would also come into focus. So focus is one way of thinking about it, but in practice what we do is we talk about photo consistency or variance in the pixels. And so this is a very useful way of thinking about stereo, that basically you have a set of points in the world and you're trying to see whether the input cameras all agree about the color, taking into consideration things like occlusions, which make the problem more difficult. So basically, it's just a reordering of the for loops. You know, classically, people might say for every pixel in the image, try all the depths, which means shifting the pixel around in the other image. But with this plane sweep, you basically say for every depth, for every plane, and this very naturally generalizes to multiple images, you then say, take all the images, shift them, and then at each pixel, compare and compute what the cost would be, the agreement would be. So that was a very quick review of multi-view stereo, which is a topic that's been going on since the 80s. Now, the basic impetus for image-based rendering, and these are slides that were created for a talk by Michael Cohen back in 1996, is that in theory, computer graphics and computer vision are inverse problems. So we take a beautiful model and then run it through some kind of a rendering system like is used at Pixar or Industrial Light and Magic, and you get these beautiful synthetic scenes, right? And computer vision, you take some images and you get a really perfect model. So you could, in theory, put this back to back, take a real scene, build a model, render it. But in practice, you know, computer vision still has problems basically rendering something like this fuzzy line with all the detail that we need. And graphics also can't necessarily capture all of the interreflections that you get in something complicated like a glass sculpture. So with image-based rendering, and the term image-based comes in several forms. One is you're starting with images, but the important thing is you're also keeping the images around to help you with the rendering process. So you take the original images and you kind of put them onto the 3D model, and then you render from that. And what that means is as you move around the object, you're using different images which have different amounts of highlights and interreflections and things like that. So you get back a lot of the reality that you get in complex visual environments. So the theory of it is that if you can basically capture all of the light rays coming out of an object, and if you do the counting correctly, you'll see that it's a 4-dimensional set of light rays. So in theory, you could take a bunch of images on a 2-dimensional array and capture all this light, and then you can resynthesize any new view you want by just picking out the correct rays. Now, it turns out that in practice, this is from our Lumigraph paper in 1996, if you have a 3D model, the ray sampling is much more accurate. So for a finite number of rays, you get fewer visual artifacts. So basically, the work that I've done in image-based rendering has always used some kind of a 3D model as opposed to like a pure light field where you only have the rays and you don't bother to try to compute some sort of a 3-dimensional proxy model. Now, the 4-dimensional space of rays is hard to visualize. If you basically only move the camera sideways from left to right, then it turns into a cube, which is a lot easier to show on a screen. And in particular, if you slice through this cube and just look at one scan line of a color image as the camera moves sideways, you get this image. The top image here is often called an epipolar plane image. And it's very interesting that you can see effects. What people who do stereo matching know is that an epipolar plane image shows you parallax because things that are at different depths move at different speeds, and therefore these lines have different tilts. But you don't only see parallax, you also see things like occlusion. So basically some of these colored streaks hide other colored streaks because they're in front of each other. The actual scene we're looking at is a synthetically rendered glass bowl sitting on a wood grain table with a lemon and a mirror ball in it and things like that. So we're seeing occlusions, but we also see all of these other interesting effects that aren't captured with a pure 3D model, like translucency. You know, you can see the wood grain, the brown wood grain, through the glass of the bowl. In fact, if the bowl is curved, then you may even get refraction, where the wood grain moves in a way that is non-rigid because the glass is bending light rays. And then we have highlights. So for example, the bright yellow streak on that yellow strip is the highlight on a lemon. And we have things like reflections. So there's actually a mirrored ball in the scene that's reflecting parts of the environment. So all of these are image effects that are basically qualitative ways of describing how pixels move and change and interact with each other. And the great thing with a light field is that it doesn't matter. You don't have to actually physically simulate each of these things. If you just want to view the same scene without modifying it, it's just adequate to capture enough images and then render them in the right way. And all of these effects can be captured. So the original Lumigraph and light field papers relied on a very regular four-dimensional binning structure. But if your images come from an irregular set of views, like somebody moving a camera around a 3D object, it turns out you can still do this, and you don't have to first rebin into a four-dimensional regular sample. You can basically take the original images, project them onto the 3D mesh, and then choose the rays using appropriate heuristics. So one of them is called the unstructured lumograph. The first author in that work was Chris Buehler in 2000. And this idea of unstructured lumograph-like systems has continued being worked on. There wasn't a lot for the next decade or so, but in the last few years, we've seen a revival with neural rendering. So for example, Peter Hedman's paper in 2018, as you can see in the diagram in the bottom, it basically takes a bunch of input images in red, it creates a 3D model in purple, which is imperfect, and then it takes the novel view, and in order to decide how to blend the pixel, rather than using a small number of mathematical equations, which is what happens in the unstructured lumograph, there's a deep neural network that is trained to basically decide how much to weight each pixel. So this is called deep blending. And this was one of the first pieces of work in neural rendering for three-dimensional scenes. As we'll see later, now very often we don't just blend color pixels, we actually use neural feature vectors to do the blending. And another more recent example of that is the free viewpoint stereo that Riegler and Colton presented at ECCB. It also takes input images and then blends them, but uses a different, more sophisticated neural blending network. Now, I've talked about sort of rays in space, and usually we think of them as emanating from either a regular set of plane or from a set of cameras, but you can turn the rays around and ask for each point in the scene, for each point on a 3D object, what is the outgoing set of rays? And if you look at the outgoing set of rays, well, they often have the same color, except for maybe a little bit of highlight that shows up when you're looking directly at, a reflection angle to a light source or something like that. So if you reparameterize this four-dimensional set of rays by basically counting all the rays that start from the same 3D point and compressing that, you get this thing called the surface light field. And it's a beautiful piece of work that was largely underappreciated. But recently, so here's an image from the original thing, and so they got these beautiful renderings of a nice ceramic sculpture. But there's been a recent revival with some of the neural rendering work. So for example, one of the recent papers is called this IDR, Implicit Differentiable Renderer, that came out at Europe's. And here the idea is use a side distance field to describe the shape. And then when you take the level set where the actual surface lies, you can feed the actual 3D coordinates and the normal vectors into a second renderer whose job it is to basically come up with the color in a way that is view dependent. So this is, as I said, many, many neural rendering papers coming out each year. This is one of the most recent ones, and I like it because it's very elegant. Now, as I mentioned, this sort of light field theory can also be used to model refractive objects like glass. The image on the right is a still from a video where we took a glass wine cup and filled it up with water and made a video. And because we had an appropriate background behind the glass, we were able to capture basically the refractive properties of the glass so that when we put a new image behind it, the SIGGRAPH 2000 image is synthetic. The glass and the water actually refract the lettering behind it in the correct manner. So this can be used for visual effects. It's a different thing. It's not a light field. It's a six-dimensional function that maps every incoming ray through a particular pixel in the image to an outgoing ray. So it's a 6-dimensional space, but it's another thing you can do in this space of image-based rendering. Other representations, there's one called the layer depth image. So a depth image is a term we invented to basically say, when you have a color image and you have a per pixel depth, we're going to call that a depth image. It's just a shorthand for colored image and depth image in one buffer. And we see a lot of the neural rendering systems use this kind of a representation. But what happens is if you have a single depth image and you change your point of view, you get gaps because you can't see what was hidden by the front object. So layer depth image allows you to store a multiple color depth combinations at every pixel. And so this was used in this layer depth image paper at SIGGRAPH 98 to pre-render a synthetic scene, and then from this buffer do very quick re-rendering. So back in 1998, we were still very concerned with rendering times, and it would take minutes to ray trace a scene with correct shadows and things. But if you could put something into a layer depth image, then you could in real time render it. So for a while, it looked like this might be the way computer graphics would go. In the end, brute force triangle meshes with texture maps and GPUs sort of ended up winning the game. So we don't see a lot of this, although these ideas are still being sort of kicked around for things called late stage reprojection, which is something that people are using to try to get the lag down in virtual reality headsets. At the same paper, the layer depth image papers, we also proposed a second line of work, which were these sprites with depth. And sprite is a term in computer graphics originally used for little moving things like Mario Brothers jumping around on the screen. Those were sprites back when computer graphics was very, very primitive. And we said, well, we can represent a 3D scene taken from a bunch of nearby viewpoints as a bunch of cutouts. And not only are they flight cutouts, but we can actually have a depth map. So the idea is it is depth images, but several overlapping depth images in layers. And we'll actually see that similar ideas have been revived and reused recently. For example, the gelato paper from Google that just appeared. And this idea of having layers reduced down to a very simple case of 2 layers is the basis of virtual viewpoint video. Now, another way to use layers is to actually use lots and lots of very fine layers. So this can be called like a stack of acetate. Acetate is the old term for things that only a couple of people like Daniel might remember when we used to do talk presentations by basically taking pieces of plastic and putting them onto an overhead projector, right? And this idea in the film industry was called multiplane images. This is what Disney used to do a lot of their animations where Snow White would walk through a forest. They would paint different parts of the forest on different glass plates and then move them. So they're called multiplane images. And we did some early work back in 1998 on this, and we had a differentiable renderer, but back then the optimization techniques weren't nearly as sophisticated as today's neural networks with, you know, stochastic gradient descent and atom and all of that. So the results we got weren't that exciting, but this has been revived 2 years ago by groups at Google and elsewhere. And now this idea of using multiplane images, so basically slicing the world up into lots of fine layers and then representing colors and opacities. So you'll see the word RGBA. This is red, green, blue, and alpha. And alpha is the opacity that tells you how to blend things at different layers. These are now very popular. So some of the newest neural rendering systems use multiplane images as their underlying intermediate representation. So here's an example from that paper in 1998. Take 2 input images, create this multiplane image. I really love the visualization in the middle because it shows you essentially what's going on. So there are color pixels, and you have to sort of use your imagination and say that the black pixels are actually empty. So think of this as a bunch of glass plates onto which an artist has carefully drawn in watercolor the various colors. And then when you move these glass plates around, you get basically in between views. So now this image-based rendering is called novel view synthesis. And so we get novel views synthesized in between and sometimes a little bit to the side of the original images. And these multiplane images have been generalized to spheres where the images are curved, which makes a lot more sense if your cameras are on a curved structure like this plexiglass capture rig on the left. So let me show you a little bit about the representation underlying virtual viewpoint video. here are the ideas. We decided to recreate what was a very popular effect back in 2000 from a movie called The Matrix, and it was called the bullet time effect, where you had video cameras in a green screen studio and then a whole bunch of still cameras in the middle, and the filming would basically be live action from one of the video cameras, and then they would immediately strobe through all of the other still images and pick up the video at the other end. And this required many, many cameras, even though they were using in-betweening between the still images. And we wanted to see if we could do this kind of thing in a more portable, affordable setup. So we had Point Grey Research in Vancouver build us a multi-camera system, 8 video cameras streaming to disks. And basically, we then ran multi-view stereo, but instead of having a single depth value at each pixel, wherever there were discontinuities, and what happens is at the boundaries between the foreground and the background, you have this band of pixels whose colors are basically in between blurs of the foreground and background. That's because the pixels are partially filled and maybe the focus isn't completely sharp. So what we would do is we would take a depth map like this, and we would basically extend the foreground and background with extra strips, and we would compute the colors and opacities at these locations and transmit those separately. So by doing that, we would get rid of these kinds of matting effects. And the final representation is quite compact. Most of the bits in encoding video have to do with encoding the color, the fine textures on clothing and things like that, or facial details. The number of bits you need to encode the depth is much fewer because a depth image is typically much smoother than a color image. And to encode these extra strips around the boundaries didn't take a lot of bits because they didn't occur that often. So we would have these extra channels, we could transmit the whole thing and then have a real-time interactive rendering system on a high-end workstation, which this day would be a low-end laptop. And you could basically change your viewpoint. And so we created this video with some local break dancers called the Massacrantes. And our 8 cameras were filming these dancers. And whenever you see the camera moving smoothly, that's not because there's a camera actually moving. Rather, it's this kind of, we're doing manipulation of cameras. Right? So we can basically use these time effects with these frames is actually enhanced with the depth image. So we can do other kinds of opacity, like for example, the person freeze them, and then show multiple snapshots of the person layered as it's called. So that's all I'll show you on the video right now. Basically, this gives you a lot of creativity. Okay. So, the reason I'm showing layered depth images, even though, virtual viewpoint video, is even though it's relatively old work, over 15 years old at this point, it kind of showed the promise of image-based rendering, taking multiple images or video streams, reconstructing as good a 3D model as you can, and good in this case means taking advantage of things like partial opacities and accounting for them, and then synthetically rendering not just novel views, but also novel constructs like sort of, 3-dimensional time-lapse photographs. I want to talk a bit about 360 video because this is another non-standard medium, but one that's kind of popular. There are a couple of places like Disney World where you can go and stand in a large auditorium and see a 360 movie. They're very compelling because you're looking at things and the sides of your eyes are seeing motion. So you really feel dizzy when you're, flying around in a helicopter. But again, we want to do this, something we could recreate in the lab with the hope that eventually this could become a consumer product. So again, we had Point Grey build us a 6-camera, small head called the Ladybug. And we put it on a tripod and pushed it around inside somebody's house. But that turned out to be very awkward to have to sort of kneel down and push around a thing. So we asked Xingbing Kang to wear it on his helmet. And when I'd show these videos at talks, people would always say, oh, that's so funny. Doesn't Xingbing look funny? Skydiver helmet with a camera on his head. Now, it turned out that just a few years later, it was really cool to put a helmet on your head and strap a camera onto it, right? So these are called action cameras. Maybe not as popular as they used to be, but still sometimes on the slopes, you'll see skiers or snowboarders with their action camera on their head. And some of them have 360 views. So this became popular for sports photography. It was also essentially what Google and Microsoft and other places used to create street view images. They would drive around vans. This is one we had at Microsoft from a group we acquired in Graz. And you take these 360 images and then you'd store them and you'd create synthetic models that then you could fly around. So if you go into Google Maps and go into 3D, most of that is done from aerial images. But if you look at the street view, you put the little person onto a street, you have these 360 images that let you sort of see, oh, what would this street look like if I wanted to rent an apartment in Tübingen or something like that. So now these 360 video cameras are really small. The Ricoh, that white one in the middle, is the one I have, and I've used it for many years when I'm out hiking or doing tourism. If I want something that sort of to remember what the scene looks like, I'll take a 360 photo. You can also get them in pairs of 180 cameras called VR 180. And there's a whole spectrum, a whole range of price points. If you want to get something where you can actually get stereo viewing, then you need to construct a more complicated rig. So Steve Seitz started this project called Google Jump, and they took a bunch of these GoPro action cameras, put them together in a ring, filmed the video, and then you could basically look at a 360 video and turn your head and you'd have a left and a right view, so that you saw things in stereo. We had a similar project at Facebook called the Surrounds 360, but these first systems, which are described in the image-based rendering chapter, wouldn't really let you look up and down and get full 3D. And in fact, if you moved your head sideways, things weren't quite rigid. And the reason for that is if you only have a left and a right eye view, you don't actually have all the pixels you need to reconstruct a full light field. So instead, at Google, we developed this fancier system using high-end industrial red cameras. And with this system, which we published as a SIGGRAPH paper, you can get a multi-layer depth image with color, and you can truly move around inside a volume with your head. There's a nice video that I won't bother showing today, but you can find it on our website. And you can really just put on a set of VR glasses and see a complete 360 movie in true depth with true, what we call 6-DoF motion, so 6 degrees of freedom head motion. So this is kind of the latest in 360 3D video. Google has a more recent version of the Jump where they basically put the GoPro cameras on a hemispherical rig. A hemisphere is actually, in many cases, more practical than 360, because with a 360 movie, you have to put interesting action everywhere and hide the cameraman and everything. A 180 gives you the ability to sort of feel like you're immersed and you can still move your head around, but there's basically a narrative. You're looking at a story being held in front of you. So this is a more recent version. Okay, and it turns out if you want to go really low end and just buy 2 360 cameras, there's a way doing stereo matching to basically simulate something that looks like a 3D 360. There are basically missing pixels where the two optical axes intersect each other. So you have to hallucinate depth at those values, but it turns out to work remarkably well. So this is kind of a low end solution. Okay. I'll say one more thing about 360 video, which is immersive video stabilization. Again, the reason I'm bringing this up is it gives me an opportunity to talk about a lot of the basic components in computer vision and image-based rendering, right? So the question here is, if you're doing something like one of these action camera things and you're climbing up a rock wall, which is very exciting, but the person you want to share it with doesn't necessarily want to sit through the 40 minutes it took you to scale this wall. What if you speed it up? So if you speed it up, you get a very jerky motion because the person who's climbing is pausing and then looking for handholds all around and then quickly moving and things like that. So what we do in order to create a hyperlapse, which is essentially a sped up video, we take all of the original cameras and create this smooth camera path. And then we use image-based rendering to put together different pieces of different video frames. And I'll show you the details a little bit more. So for every input video frame, we use multi-view stereo to create a point cloud, and then we turn it into a mesh. So each input image now lives on a 3-dimensional mesh. And after we've basically taken the mesh and we want to re-render it from a new viewpoint, we don't necessarily have all the pixels we need. We can't just take a single image and warp it in 3D. with the mesh because the person may have been looking somewhere else. So you actually have to steal pixels from different frames onto the mesh, put them together, and that's how we get the final result, right? So this is sort of a spatiotemporal stitch, which in color shows you which frame each pixel is coming from. So you can see we're basically cutting out and gluing together pixels from many different frames to get something that looks really smooth. So here's an input video. This is bicycling. So you might think, oh, okay, it's bicycling. I don't need all of this sophisticated hyperlapse stuff. But if you speed it up, it turns out there's enough jerkiness in the basic bouncing and looking around that unless you do the hyperlapse, which is our result here, which sort of looks like it was a smooth drone flight, it's unwatchable, right? So this is the kind of stuff, it's not just for action videos, but for regular videos. And the reason this paper is very interesting is if you dig under the covers, it has a whole bunch of state-of-the-art 3D reconstruction and image-based rendering, like stitching and blending components. So it's a great way to kind of learn about the basics of image-based rendering. Okay. I'll mention a little bit about large-scale reconstruction because Daniel in his introduction mentioned the phototourism project. So here the idea is rather than having one videographer take a video or one person in the lab set up a bunch of cameras, right? There are all these photos on the web, on the internet. Now they're called crowdsourced photos, right? So back then in 2005, when we started the work with Noah Stavely and Steve Seitz, there was a web sharing site called Flickr. Now most people share their photos on, you know, Facebook or Google or WhatsApp. So we would take the publicly visible photos and say, can we create a 3D model and a virtual tour of a location? Like here, this is Notre Dame Cathedral. So classic 3D computer vision will let you build a 3D model. But what we wanted to do was kind of build an interactive photo explorer that lets you look at the original photographs, but feel as if you're immersed in the scene and flying around. So this is what our interface looked like. You could click in the top-down view and basically say, move my virtual viewpoint to this point on the fountain. Or you could basically highlight a region in the image that you're looking at and say, give me a zoom in of this, or move left and right. If you look carefully at the transitions, what's happening is there are these billboards which are oriented with the dominant planar structure, and the images are projected onto the billboards and cross-faded. So very much like when I talked about plane sweep stereo, this is the opposite. This is taking planes, projecting the images onto the planes and cross-dissolving them, right? So it's a very low-tech image-based rendering system, but it gives you just what you need to be able to basically move from one image to another in a way they feel like you can explore what would otherwise be a jumbled set of photographs living as thumbnails on a page. This idea of piecewise planar proxies can also be used as part of the reconstruction process. So here, in addition to the classic point cloud that people often use, we actually extracted a set of parallel lines and had a line cloud, and from the line cloud that told us what the plane hypotheses should be. So you can also build these kinds of local planar models. And as I mentioned earlier, there's this recent Gelato paper from Google that does the same thing, but in a neural rendering context. Another thing you can do is if you're not sure about the quality of your 3D model, you can basically use a mesh model in the middle, but then use a point cloud outside of that. So the middle part is using classical image-based rendering with a 3D mesh and projecting images. But the background, because the quality of the mesh, if you try to reconstruct the background, would be really incomplete and spiky, we just represent it as a point cloud. So you sort of get this combination of the world as a point cloud and the actual photograph, the part of it that is accurately reconstructible as a 3D model. Okay, and more recently, there's this photo tours from Google, where basically they take landmark photos and do 3D transitions using actually local texture maps. I love the way the camera moves are done here, so that basically you have a quick transition between images and then a slow rotation and camera pan to give you a sense of three-dimensional. And these things were working so well that Qi Shan, at part of his thesis, one of his papers, asked the question, can we do image-based rendering to the level where a viewer can't tell what the original image is and what the photograph is? So in each of these images, you have a left and right pair that is an original photo and a synthetic rendering. And your job would be to guess which one's which, right? And again, it's not an interactive talk, so I can't have a show of hands. For some of them, it's obvious by looking at things like the background, but in other ones, it looks very, very close. So this was sort of a sanity check to say, how well are we doing with image-based rendering? Now, from internet photos, we want to be able to bring this back to something where a single person could take an image. And we developed a system called casual 3D photography, where you would take a series of photographs, and from that, we would extract a depth image and a normal map. And the normal map allowed us to do synthetic lighting effects. And this whole big offline system that ran on your computer, and then essentially created a 2-layer model where basically you had a front layer and a back layer, and then you could do this kind of 6th degree of freedom viewing experience of a place that you visited, maybe your childhood attic. And so these were some of the kinds of 360 things we reconstructed. You can also do it, you don't have to do a full 360, you can just move your camera around in a local space and get a little 3D photograph. But this took a lot of offline computation, a lot of multi-view stereo. It turns out that the cameras, starting with the iPhone that had the dual lens, started computing depth maps in order to do synthetic refocus and depth of field. So if you get the depth map from the camera, you can do this a lot faster. Now, the depth maps turn out not to actually be metrically accurate, so you have to warp them a little bit. But you can do this and get a system that runs much quicker. And so we developed, this was published as a paper, workshop paper 2 years ago. And this is our practical 3D photography, where we take the depth map, do a little bit of inpainting on the background, and then view it in your Facebook feed. And so these are what some of these 3D animations look like on Facebook. You're basically, as you're moving your camera around, it looks 3D. Here's one that's more sophisticated. And that just shows what the quality of the depth map is. But in addition to the dual lens cameras, people were working on depth, mono depth, where you basically would take a regular photograph and create a depth map using neural networks. So now we can do this for regular two-dimensional images. And so this was published last summer as one-shot 3D photography, where the depth estimation, all of the computations are done on your phone now. And so you can basically take a regular photograph with your camera, build a 3D photo, preview it on your camera, and decide if you want to post it. So this is now a regular feature. This is another CVPR paper showing historical photographs with much more sophisticated in-painting from Jiabin Quan and his students. And Google also released a similar thing. It's a little subtle, but if you look on the right-hand side, you have an image that is in your photo album that has this sort of synthetic looming effect. So they call these cinematic photos. So I am running out of time quickly, so I may have to kind of skim through either reflections or neural rendering. I think I'll try to go for another 5 minutes. Is that okay, Daniel?
Yeah, it's perfectly fine. Go ahead.
Okay. So I wanted to mention reflections and transparency because for a lot of scenes, like, things in glass museum cases, or even a table in your house, you see reflections. So you might say, well, this is a special case. This only happens in museums. But as a viewer, if you're sitting right now at your computer watching this video, look around, look at your cell phone, which has a glassy surface, look at your laptop, which maybe has a matte finish. Reflections and gloss are pretty much everywhere, and they can get very complicated on curved surfaces like car windows, and you can see through the car and you can see reflections. So this is something we need to model. But if we use a standard image-based rendering model where there is one geometric proxy that you're trying to map the original images onto, things jump around. The bottles have the right depth, so they move smoothly, but the reflections are at a different depth, so they jump around. So the solution, and here's our new system that we developed, is to actually have more than one layer. So what we do is we extract multiple layers. In our case, basically, we're talking about single reflections from glass. So we extract a front depth layer and what we call a rear depth layer, which in this case is the reflection of a staircase seen behind you. And then we also extract the color that goes with each of these layers, and we put them together to generate the novel view. Now, putting them together requires you to modify the traditional overcompositing, which attenuates the light coming through from behind, and use a pure additive model. But if you do the right thing, you can get these kinds of things. So we had an initial paper doing this. We had a follow-on paper which does this in the gradient domain, which basically means that we compute, instead of a complete depth map, which is very hard to do, we just take the gradients, the high edgy parts, and we compute the depths at those locations where things really separate nicely. And then we can move the gradients around, put them back together, and create these kinds of renderings with reflection. So if you look on the right, it's a very complex image. There's a high resolution poster in the front, in the shop window, and also, you know, behind that, there are the lights of the shop. And then there's a reflection of the town behind that. So this is a way of doing image-based rendering when there's a lot of two different layers. And I think this is a very promising future direction. So you can use the same kind of thing to do remove obstructions, and you can also do it in camera because cameras have 2 pixels, dual pixels. So you can look at the gradients and say what the depths are at these pixels, and then automatically remove from a single image the background and the reflected. So this is work I really like that showed up 2 years ago. So there's more work to be done in this area, but basically including things like curved surfaces. This is work from Mark Polyfie's group. But I'm not going to have a lot of time to talk about our neural-based rendering work, but that's okay, because I think you've heard a lot of neural rendering papers recently. I just finished, you know, these are some of the talks. If you haven't seen them, you can go back. These are all talks in the lecture series where people are talking about various aspects of neural rendering. There's this wonderful tutorial from CVPR, which basically categorizes, groups things by application area. So whether you're doing photos or people or novel view synthesis or relighting or free viewpoint video, which is more outside in 3D performance capture. I just finished writing my section in the book, and I decided to categorize things into 4 different underlying representations where you're using 3D models, or you're using these kinds of depth layers. This is the billboard, the gelato work I mentioned, or you're using voxel grids, or the most recent thing that's very exciting are things like these implicit functions, NERF, IDR, all of that. So I won't be talking a lot about those. I'll just mention 2 recent pieces of work that we did. One is called SynSyn, end-to-end view synthesis, where the idea is you start with a single color image, you hallucinate a 3D model. So that's basically down here, you get a depth image, and then you project the model into 3D, change your viewpoint, and then reassemble the image from these neural features. So I mentioned that when you have a single depth and color, you get gaps. But the beautiful thing about using neural features is the final reassembly stage, this decoding network G, can take something which is an irregular set of neural features and learn how to produce a coherent photorealistic color image. So this lets us do things like take a single still image and then do a synthetic pan. So this is a good example of sort of the newest style of neural rendering, where you use neural features inside to represent the appearance. And then you do a final decode, which gives you an image that looks photorealistic. And this inspired us for the newest work, which is animating pictures with a layer in motion, where basically we can take a single still image and turn it into a video clip like this. And the architecture looks very similar. We basically, instead of hallucinating a depth map, we hallucinate a motion map. We take the neural features, we move them around by basically tracing the motion paths, and then we decode it. So that's the basic architecture. And Daniel, I'll do a time check again. Can I have 3 more minutes to show the video for this? What do you
Yes,
think?
go ahead.
Okay.
Sure.
So
When we see a picture, we can often guess
let
how
my
the scene was
author,
moving when the picture was taken.
Alexander Szeliski, talk a little.
If you look at this picture, you'd probably guess the water is flowing outward, right? And you'd be right. And you know this because images contain subtle details about how things should be moving. For water, this can be the direction of the ripples, the amount of turbulence, or even motion blur. In this project, we teach a computer to accomplish the same task. Given a single image, we predict the motion in the scene and use that motion to animate a looping video. This video is the result of our system, generated from only a single image. So how's this done? First of all, we need to consider what the right representation for motion is. We're targeting fluid textural motion, like what you'd see in a waterfall, river, smoke, or clouds. And all of these are fluids and are well approximated by particle motion. So we use an Eulerian motion field, which can also be thought of as a particle velocity field, and it defines how a pixel at every given location should move. That is, a single motion vector per pixel. Using this information, we can animate a pixel, like this green one, by following the path that the motion vectors define. And this process is known as Euler integration. This representation allows us to produce very complex motion paths, but only requires us to estimate a single motion field to generate the whole video. So we've collected a couple thousand stock footage nature videos, and we use these to train an image-to-image GAN to predict the motion field from a single image. We then use this predicted motion field to animate a video. If we were to do this naively, by splatting the color image using the predicted motion, we'd get artifacts and holes. So to avoid these, we use a deep warping technique with a novel symmetric splatting approach. That is, instead of warping colors, we encode the image's deep features and warp those to a future frame. Then, we use a decoder network to turn those warped features back into a color image. This fixes artifacts, since the features encode local contextual information about the region which is being warped, and the decoder is trained to produce realistic texture. However, eventually we'll still end up with really big holes in the warped feature map, which will show up as gray, unknown regions or as blurry, flickering regions, since the decoder is working with very limited data and can't produce reasonable texture. We solve this using a novel symmetric splatting approach. We rely on the insight that fluid textural motion isn't transient, so we can feasibly borrow content from different points in time, like a video animating into the past, to fill in these holes. In fact, warping our input image into the future and the past gives us animations that have complementary holes. So our symmetric splatting technique works by jointly warping both of these to the same destination image, effectively eliminating holes in the warped feature map. Additionally, the future and past videos have a convenient property. One video starts with the input frame and the other ends with the input frame. In the paper, we describe a method to fade the contributions of these two videos so that we automatically get a video that's perfectly looping.
Okay. I'm going to skip the training part because I want to wrap up. So basically, today I've talked about the history and some of the basic principles in image-based rendering, and also some of the applications, which are both commercial for things like sports games and movies, but also consumers, where you can basically take 3D photographs now with your camera. I've mentioned that reflections and transparency are an interesting problem. There's a related thing which highlights. So if you look at the Nerf paper and you have a little plastic Lego model, you can't model that as two layers because the geometry is too detailed. So it's actually much more useful to model it as something like a light or radiance field, where you have a 3D model and then you basically model the highlights as a separate thing. And I've mentioned some of our recent work in neural rendering. So I'd like to thank the organizers for organizing the whole series, which is wonderful, and for inviting me to speak. And at this point, I'll be happy to take any questions. Thank you.
Thank you, Rick, for the wonderful presentation. It's been really amazing to see all this historic overview of image-based rendering, and to also see that your work is very much at the source of many of these developments. And so I think it's safe to say that image-based rendering would not be what it is without your contributions.
Thank you.
Really amazing. Do we have questions? Yes, I think Björn, you have a question?
Yes, I'm just gonna forward the YouTube questions.
Mhm.
So Juan Raúl Padrón Grif asked, first, thank you for the fantastic talk. Which do you think is the direction more promising? Focusing on improving the existing reconstruction pipelines or fixing them with neural rendering?
Oh, that's a great question. I actually hadn't thought of it. I was late to the neural network game because initially a lot of the initial results were on very limited domains like ShapeNet or Kitty, very closed worlds. There's an interesting thing if you look at a lot of this work in image-based rendering and light fields and so on. It's capturing a single scene under particular illumination conditions and then re-rendering it. Now, there are these newer works like, neural rendering in the wild, which take photographs at different times of day and they model appearance and so on. Partially, it has to do with manipulation. If you really want to, if you want to composite a scene where you're going to take 3 different complex objects and put them together on a table and then animate them and create a movie from that, you really need more control. So you need better 3D models, right? The neural rendering is a great way to fix things, but so far all the examples seem to be very limited in scope in terms of application. So for our animating fluids work, we really only trained and tested on rivers, waterfalls, smoke, and clouds, right? And we believe that by taking different training examples of, let's say, leaves rippling or things like that, we can extend the technique. But it's mostly going to work on textural things that are largely stochastic and can be represented in that kind of way. Another piece of work in neural rendering I really love is PIFU, the pixel implicit functions, but that's specifically trained on people wearing clothes, fashion models. And for that domain, when you give it a new image of a person wearing a model, fashion, it creates a beautiful 360 view, right? So I think the danger with neural rendering and neural machine learning techniques in general is that you can memorize a particular class of objects and it's great, but when you go outside of the domain, the performance isn't predictable, right? So, if this is sort of like advice to a student, like which area is worth working on more, I think they both are very important. And getting more and more detailed things, so being able to actually model thin structures consistently from multiple images will still be important. And of course, the hardware itself is a moving target. How soon are we going to get cameras that have more than one lens? Well, most of the new ones do, because they want a telephoto lens and a wide angle lens. But as the costs drop, we'll probably start having planoptic cameras with lots more lenses. And so that'll do a lot of the heavy lifting for inferring 3D depth from us, right? Or you can start with RGB depth cameras like Kinect and other ones, Intel. That's another powerful source. So there's a rambling answer to the question.
Rick, one question about your very last work here is really amazing. And this is, I think, typical of a lot of deep learning based approaches, that there are parts that you use neural networks for, and then other parts where you do, say, more classical modeling of motion integration, etc.
Yep.
Obviously, one alternative would be to do a complete end-to-end learning approach where you train a network to generate videos. Say, if you have examples of videos and still images, you could easily try to train a network end-to-end. Do you think that is a good alternative, that we completely ignore the motion modeling and just have a network hallucinate the video?
Sure. It's a great question, and in computer vision, we're always going back and forth about, how much do we architect? What's and how much do we let the system learn end to end, right? So this system is an end-to-end learning system, right? I mean, it basically, all of the weights in the motion synthesis network and the encoder and decoder are learned and are completely, back propagated. So it is end-to-end learned, but by hand, we decided to put in this idea that there is a motion field, and that the motion field applies a particular mathematical formalism that basically takes each pixel and moves it somewhere in a chained fashion, right? And before we had the Eulerian integration, where we just basically took the velocity and extrapolated it, it didn't work well, right? So there was this insight about Eulerian motion. So the question is, could you have a similar system where you remove the motion synthesis and this displacement field and the symmetric splatting and just basically have images in, images out? I think for certain things, like let's say leaves moving around on a tree, it's stochastic enough that essentially, even slightly nonlinear stochastic noise models could probably do that, right? But if you really wanted to have something that models the ability to capture spinning record player discs and pendulums and things like that, the network would have to train for a lot longer to implicitly learn that there is coherent motion. So my general philosophy is, if there is physics in the world and the physics is correct, as computer vision people, we should be wiring that in, right? Because then the network has to learn less. What it has to learn is the fact that there's no easy way in physics to describe the appearance of bubbling water, right? I mean, you have SIGGRAPH papers that do bubbling water ad initio with particle systems, but they're incredibly cumbersome. And so for a lot of things, if you can get it down to something which is statistical, the learning is much better than trying to completely simulate it. But for physics, for example, I think one failure of an end-to-end neural system is instructor from motion. Some of the original pose regression things ignored geometry and turned out they could only essentially interpolate between given views, right? So when we have physics and mathematics and it works, my general tendency is to wire that into the system. But that's just my personal preference.
No, I think I totally agree with that. And I think the more physics you can bring in, the more the systems will generalize beyond the observations somehow. Yeah, good point. Do we have more questions?
I can ask one question, actually.
Yeah.
Well, obviously, it's super cool, I think, specifically for new students to look up your work and think about how to combine it with the deep learning stuff, right? Like make it neural coding. I'm curious, what's your take on video chat right now? Why do we still have 2D video chat, and why, even in this constrained setting, what's the limiting factor to have a better experience, like viewpoint synthesis and stuff like this, right? We don't have that yet. What do you think is the limiting factor?
It's a great question. I mean, there are limiting factors in 2D video chat. The Zoom call today is wonderful because we're not getting any lag, right? But I've been on Zoom calls where you get, 40 people on one call, and it's just like, it's somebody. So there's basic technical limitations, which, as bandwidth increases. But 3D is interesting, right? In particular, if you said, can we do the 3D talking head, the magic mirror, the fishbowl VR thing, right? There are some physical constraints, which is that, first of all, to view things in parallax, you usually have to wear some colored glasses, or you can have, the barrier displays. So we could hypothesize having 3D displays, right? And I think the cost of having, let's say, 4 or 8 cameras around the periphery of your monitor, encoding that on your laptop to something that's a 3D video, transmitting it. And I'm not even talking about using codec avatars like, work that you're doing and Yasser Sheikh and things like that. But I think just the bandwidth compression that would let you not just do a talking head, but also hold up a puppet and hold up a teacup, and it would all work because it's just doing multi-view stereo. I think it's possible to do those kinds of systems. It's just that deploying them so that everyone has it on their computer and phone, the way Skype and Zoom and Messenger and all these other things are, they become more useful when they're ubiquitous, right? Now in professional settings, we could certainly do that. And I think given where we are now compared to some of the early experiments that computer graphics labs in the 1990s did by having portals between their rooms, I think there's no reason not to revisit that. If I was going to build the system, I would heavily invest in more cameras and multi-view stereo and put the neural nets into building a 3D model, and then having some kind of neural renderer at the end, but it would have multiple layers and you could do background subtraction. So I think the technical limitations are basically we can build proof of concepts today, and some people are, but making it deploy widely, like you could ask, why weren't people doing video chat 10 years ago? We could basically do it. We could do it, those of us who are in labs, right, in the major universities could do video calls, but no one could. It just takes a while for the technology to percolate down to a cost point where it's ubiquitous.
Yeah, thanks a lot.
I think we have another question on YouTube.
Yes. Abdullah Saouli asks, so in 3D reconstruction, we can evaluate results based on geometric accuracy and completeness. What about novel view and image-based rendering?
Great question. Yes, this evaluating things with the geometric accuracy. I think Vladlen Colton with the tanks and temples data set did a beautiful work. I mean, there are related things like the DTU data set and so on, but the tanks and temples, they really came up with a good metric for geometric completeness and accuracy and things like that. For rendering, it's interesting because just doing pixel to pixel comparison is hard. Like when you say, is my waterfall better than your waterfall? They're both going to disagree at every pixel as to what the color is, right? Because they're just waterfalls. So how do you evaluate it? Well, we have perceptual loss and those things. And then we have user studies, which are painful, but a lot of SIGGRAPH reviewers seem to require a user study to back up any quantitative measure, right? So the answer, I don't have a clean answer for how do you evaluate renderings and neural renderings, right? Because in many cases, you're not recreating the original image, right? That's one of the beautiful parts of neural rendering is you're creating something that looks like the original image, but obeys a perceptual loss, which means that the textures are approximately in the right place. And you can be more sophisticated than evaluating individual frames, right? If you're doing an animation, you don't want it to flicker and change appearance. So you can have things like temporal consistency. So, we've been kicking around things like that, metrics that we use internally as we develop these techniques. But I haven't seen any kind of a gold standard. Right. So the best I can do right now, and what I do in the book, is point at some of the recent perceptual metrics, which include, like, I think there's a Europe's paper recently that marries a classical perceptual model with a neural network. So, yeah, it's not an area I'm really an expert in.
All right. I think we have no more questions from what I can see. This was really amazing, Rick. Thank you so much for your time. Thank you for this wonderful presentation and the very exciting Q&A discussion. It's been a pleasure.